So the item now, according to our program of the day, Marcus will be delivering a presentation as shown on the screen over there. So just a quick introduction about Marcus. Marcus is a load research specialist. He has been involved or been active on the subject for around 25 years. He has also contributed a lot on the development of the NRS 034, or which we know now as SANS 547, as a project lead. Thanks, Marcus.
I'm going to be talking to you about non-domestic load models. And the whole point about the load models is that I'm going to be telling you a story. And the story started basically in 1999, roughly. A group of us were sitting in a meeting with some ESCOM planners, and Ed Bongi was there and some of the other stalwarts. And the idea of a totally integrated planning system was raised. And I think Lloyd Jones was there as well, and he said, maybe you guys can give us a hand. You load researchers, you're busy. You've been going with this domestic load research now for 6 years. Maybe you should turn your hand to industrial and commercial load research. And of course, we said, naturally, where's your data? And so that's how the story started. I'm going to be talking in the story. I'll tell you what we've done since 1999, what we found, tell you what the current state of the industrial and commercial load research is, and talking about perhaps the next steps where we need to be going in future. So in 1999, we had the TIPS under development, and it was really just an idea, a concept. But we were a very enthusiastic group, and so we dived in. We started to look at design documents and start to say, well, if you wanted to have a planning system that had, where you could do all of your line designs and your master planning in, what would you have to do? Well, first of all, you'd have to be able to add up loads with uncertainty, certainly. You'd have to know quite well how to handle uncertainty on the loads, because it's the mean plus uncertainty gives you your peak value. So you'd have to have a good handle on covariance and correlation between loads, and how to assess the system error. If you are going to go into a planning system and it means that you're going to have to develop load models, then you've got to understand what the impact on your system error, your planning system is for having those load models. And you'd probably have to understand how to solve a load flow with uncertainty. And to date, I don't think we've done that yet. It's interesting. And we'd probably also have to understand what a load class is, because planners need to deal with these finite things, which they then multiply by a number of those. So it's a finite thing times the n of that thing gives you your load. So we'd have to understand what that base thing is, that what we call a load class or a load shape. How would we predict a load profile? And that's simply by adding up the loads that are hanging under the network as load points and as customers in an area. And we'd also have to understand what the impact is of time resolution on our load models. And I think Justice will have a word on that a bit later. So, a fundamental question really is, what is a load class? So we started to draw a block diagram, and this is the actual thing from 1999. We said if you're going to have a planning system, then you're going to have a load profile resource, and it feeds into some definition of a load, and you've got some plan time datum. In other words, a date time, like a year 0 and a year 1 and a year 2 that you push this thing through, and you must be able to manage a forecast. So you've got to be able to handle a load profile with risk, and the profile must add up as you move to the higher levels in the network. And so you end up with your profile summated at a higher level. So that then asks the question is, if this is sort of how the thing would fit together, how's the load defined? We didn't know. We simply didn't know. How do you forecast a load over time? Again, fortunately, we didn't know this was not possible. We didn't know that either. And how do you get a planning system to run quick enough? Well, the way that you get it to run quick enough is by not using the real loads. You must use load models. It's as simple as that. So here's an example of a daily load profile. And this is, as you can see, for a domestic customer. And your typical planning thing is that you want to be able to forecast this load profile eventually. So how do you do that? Well, you've got 87650 hours per year. You convert it into a load model. And here's an example of the profile before, and it's now being converted into a load model with a mean value and an uncertainty on it. And once you convert this load into a load model, then all of a sudden you can see that you've actually got serious data compression which has happened. Your load profile now represents a number of similar days, and you've got an uncertainty on top of that load profile, or standard deviation, which is the repeatability of the behavior of those customers. And that contains some information about the load profile, about the risk on the mean profile that you're showing. So the load model gives you some compression, and the differences in the behavior day to day are contained in the uncertainty. And you can define it as is convenient. And that's actually what we did. Now, if we look at another interesting thing about the mean profile with uncertainty is that you can use that as a definition for your peak. You can say your mean profile plus so many quanta of uncertainty or of standard deviation gives you your peak value. And that's how you can sort of put a risk on the peak value. And you can ask that question in reverse. You can say, if I have this peak value, what were the chances of me, what was the risk on that? What was my exposure on that? So if we work with the mean profile and an uncertainty, then we preserve the uncertainty in the load profile models and calculations, and we can work with that uncertainty all the way up as we add those loads up to higher levels. And we can work with known risk levels. Okay, so let's look at what we're doing here. We're adding uncertainty. Just say that we have two load profiles and we want to add them together. And we're working with two random numbers, basically. So if you add your uncertainties for two independent random numbers, say x and y, then you get a formulation like you have, two random numbers. I'm not saying whether they're dependent or independent. You get a formulation like is shown in the second line down there. Your total standard deviation is equal to the sum of the squares of the two standard deviations, and then you've got your correlation, that's the row term, and then there's a sigma x and a sigma y. So that's the individual standard deviations of the components. And that's how you arrive at your standard deviation for the total. Now, if your uncertainties are not correlated, then your correlation term, that row, goes to 0, and you end up with sigma squared y is equal to sigma squared x plus sigma squared z, which is your standard formulation for independence, right? And if you have some measure of dependence, then your row term is non-zero. And off you go again, and you get a value which is somewhat larger. Does that make sense? So once you've got that dependency, you can get quite a substantial change in your uncertainty of your sum when you're adding two profiles together. Now, another way that you can get virtual independence is if your standard deviation of your x and your y are both rather small numbers. So if your load profile for x and y is quite small, then the multiple of those two gives you a small number as well. And that's what we basically use in the definition of load models. So if your correlation is small, you end up with a small interaction, and if your uncertainties are small on your profiles, you end up with a small interaction. So let's have a look at where this takes us. Just a view of correlation or dependence. On the left-hand side, we've got a plot between the term x and y, and you see it's basically a cloud, so engineering, nothing really solid to work with, low correlation. Although in my early days, I would have said, oh, there's something to work with, yeah. Because we didn't have a lot of data, right? Okay. And on the right-hand side, that's what we'd like to be used to. We'd like to see that we've got the terms of the right significance and so on. But that is typically what you see when you've got some dependence between the terms, and if those are two customers, you see that those customers are kind of moving together. So they're roughly the same kind of customer, and they're responding to the same kind of external stimuli. And that stimuli might be air temperature, might be public holidays, or time of use tariffs, or something like that. All of those things can give you an item like you see on the right-hand side. So local customs, tariff signals, stuff like that will give you some form of correlation between your customers. Why is it important to know whether you've got correlation between the customers or not? Because the correlation determines what happens to your risk when you add your load profiles together. If you've got correlation, then your risk is going to blow up. So let's have a look at what we found when we started to study domestic customers. Now, it's a pity that Schalk has left because he did this. This is for some customers domestic customers in the Durban area. And this gave us a clue about how to approach the formulation of the load models on the industrial and commercial side. We took the evening slot between 18 and 18:30 on a weekday in August. And then we investigated all of the customers at these various sites where we happened to be monitoring in Durban. And we then did some simulations, and we started to figure out what the correlation actually was like and what it wasn't like. And as you see in the intersection between lotus X and lotus Y, that 0.44 there is the correlation of the customers in lotus to themselves. Very interesting. If we look at the correlation between the customers in lotus to any other place like Umgaga, Umlazi, or Orient, the values are rather lower. So here we have customers that are roughly the same, and they're all in the same area, in the same 20-kilometer radius. And what we're finding is that the customers that are really close together and are defined roughly the same have significant correlation to themselves. Customers that are nearby each other, in other words, subject to the same weather, they don't behave the same. And so they have rather low levels of correlation. So why customers behave like this, we don't exactly know, but it may be possibly a function of geyser controllers, and that's a contributor, or they simply have similar customs and habits, access to similar appliances, they watch the same TV shows, and that's just how they roll. So however, the patterns are strong enough from our point of view for engineering purposes, and if some simple assumptions made, then the root of a load class is living here. Correlations between classes we can actually practically ignore. If we're looking at domestic customers, you know domestic customers move appreciably with environmental stimuli, temperature, sunshine, stuff like that. And if we define them closely, we can ignore it. And if we use representative value of correlation, then we sort it out. We work with the stuff on the diagonal, and we ignore everything which is x to y. And that basically led us to the general rule for profile classes. What we said that was that we'll define a load profile class as a group of customers that exhibit the same behavior, share the same technologies, have a similar load shape, and thus respond to external stimuli similarly. So we define them closely enough that they behave similarly. In other words, they've got a strong diagonal. Also, one of the other factors that we took into account was that, you know, when you're working with master planners, they are actually rather bright. But if you give them too much to play with, then they'll play too much. So too many load classes can be counterproductive from an industry point of view, because it's actually hard to make a choice when you give an infinite choice. We can't have knobs. We must have clicking devices, and the number of clicks we can have should be reasonably well controlled. So there was a principled decision made. Thank you. To limit the number of load classes, and so that was justifiable, and we needed to look up those load classes by business rules. So that was all sorted out. So we focused on a tight definition where load planning was most crucial for the average winter. So we said for planning purposes, it's really important that we sort out the nature of the planning problem for winter weekday only. That's where we want our accuracy to be. So we filtered. We started working on the load classes. I'm going to flip through this a bit quicker now. But we filtered. We started with a set of about 9,000 to 15,000 customers and whittled it down. We ended up with about 9,000 customers in a particular year. We normalized the load classes, the profiles of those customers. And so we had a set of 9,000 customers, which are normalized with energy. And we then did some shape clustering on them. We filtered them by the SIC code, the Standard Industrial Classification Code, down to 1 or 2 digits. And we went through a clustering exercise. In other words, what shapes are most similar to each other and less similar to adjacent shapes of roughly the same description. And then we pruned the tree for practical purposes. And after that, we documented the derived classes carefully. Through that process, you know, if you're saying 9,000 customers, blah, 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 you're not going to get every single SIC class that does exist, and some of them are not practical. So here is an example of a load cluster, a cluster of load classes as we actually derived it. So on the right hand, you can see that the shape is roughly a tree, and you have a split. You have a split here, and that accounts for some portion of the difference between this family of load classes and this family of load classes. And so we started to apply wisdom, and we ended up with a name set of load classes by separating the families into readily identifiable types of customer, which then had a number of attributes. And here's a result of a pruning on the load class. This is the actual load class of 1A. And this has got vital statistics. You can see it's got a high season weekday, high season weekend, low season weekday weekend, and then there's some stats on the power factor. Okay, so The result of this was that we ended up with 20 distinct non-domestic customer behaviors, and we defined them in very great detail. Load density, behavior at the peak, behavior at other times, how those customers are described, then the business rules, what SIC classes go into those customers, and so on. And the behaviors that we have do not cover the whole range of customers, but they are very good for the ones that we have. Now, this set of load classes was developed from the ESCOM large power users, so all customers greater than 5 MVA. Now, subsequent work that we did, we derived limited regional load models that we found to be significant and linked to climate and biomes and regional borders. We developed a separate set of load subclasses that had local flavor to them. And also, we evaluated the load modeling system error. And now we actually have almost come around in a circle. We said, what was the price of using a load model instead of using real load data to do your planning? This is where we came back to the question. We've now developed the load classes. We've produced a library of non-domestic load classes. And now we've gone right through to the other side, and we said, what is the price of evaluating the load classes? And this is the way we did it. We took real loads into a simulation tool, and we took the load models that were derived from the real loads into the simulation tool. We put it through a sample of networks, short, medium, and long feeders, that were typical out there in the planning sphere. And then, because we had the real loads and we had the load models, we could now complete the planning problem, estimation of the total load on the feeders, by using the load models or using the real loads, and compare the results. So that gives you the price of your load modeling, basically. And we were able to do that, and it gave us a couple of interesting results. One thing was that we were able to estimate using this sort of technique the system error for short, medium, and long lines. In other words, does your error blow up when you're dealing with short lines and low number of customers? Does it ease off with longer lines? We were able to answer that and give quantity to that. We were able to also identify the impact of load model aging. One of the very interesting things was that we had load models, loads from a particular time, and load models that were developed at a particular time, but then we also had the subsequent loads, and we could compare the old load models with the new load behavior. And we were able then to see what the impact was of the aging of a load model, the change of customer behavior with time. And it was significant. We put a number on it. We were also able to evaluate the impact of residual correlation in and between the load classes, because we had real stuff and we had real loads and we had the load models. We were able to check now what the impact was purely due to the definition of the load models. So now we're actually back at the beginning. I said in 1999 we had a whole list of almost questions that we had when we were trying to set up TIPS. Now most of those questions actually are partly answered. We need to move on, but we have done the groundwork and we've got numbers now. Those questions are answered. I think from our point of view, there is future stuff that needs to be done. We did this development of the load classes, the load models for industrials and commercials, but that needs to keep track over time. So we need to be doing a revision of these load models with time. What we said is that we have actually we've quantified the cost of aging on load models in terms of your system error for planning. Now we need to keep track of the aging and manage it over time. Also, we need to be tuning load classes to reduce our system error. We found that in the definition of our load classes, we were picking up a small amount of system error, and we need to be tuning the clustering and the pruning to make sure that we reduce that system error. So another issue from a future work point of view is the derivation of load subclasses for small power users. This is akin to using a large CAT, which is load subclasses developed from large power users on small customers. Does that actually work? If you shrink a load profile, does it look like a small power user? A large power user load profile, if you shrink it, does it look like a small power user? We don't actually know. And that is just a white space in our knowledge right now. The amount of knowledge we've got on small power users in South Africa is rather dim and sad. So we really need to be developing load class models for SPUs, because the bottom line is that in South Africa there are many overhead lines that only have small power users, and line designs are being done using large power user load models. And I think a broader derivation of load classes needs to be done to satisfy the South African market. We're talking here about Eskom customers, but there are many other customers in South Africa, in the quasi-government, in the municipalities and local government and so on. And we don't know enough about them and how they behave with their tariffs that are applied to them. So the work that we did with the non-domestic customers was put into the Eskom GLF manual, and it basically immediately became an Eskom standard. That's where we were. There was nothing else. And this is the first or the second edition of that, which is in documentation now. I'd just like to thank, firstly, Lloyd for his long-suffering observance of our research efforts over much time. Lloyd, you did make a lot of it possible. Thank you for running interference while we worked. And then I'd also like to thank the research team. Schalk, pity is not here, and Jacques Boyson from NOA-BOH. He contributed a lot to the data crunching. Okay, thanks. That's it from my side. Questions?
Any questions for Marcus? Marcus, what was that sort of range of that system here that you mentioned the different classes?
That's quite a broad question. I probably need to show it to you. I can send you an email on that. Yeah. Thanks. To me, it was very interesting to understand kind of the whole error budget side of it and where the errors were coming from. Because when we started, we didn't really have an idea, and later on we were able to tie together at the back.
Did you actually see or notice any correlation in terms of diversity with the various demographics in terms of food supply? In other words, you've got your load classes, and if they're similar, did you get a better correlation in terms of diversity, or did you see any of those things? Or you just treat them all as maximum power, no diversity, all using their own capacity independently?
No, I think what we're seeing is that the way that we designed the load classes, what we were seeing is that we'd have high correlation within a class and pretty much nothing outside. That's what we were going for. Does that answer your question? I guess that's the inverse of what you're asking.
So if a developer puts in a township and he's got a particular demographic in mind, small SPU type thing, 2,000 square meters, World Bank standard of 140 kVA, they will all be very similar in nature, in terms of their load requirement.
Yeah, the way that we define the load classes for you're taking it to domestic specifically, but for domestics, we'd expect what we're seeing here is that the correlation within is roughly about 0.5. And the correlation between, in other words, to different classes of consumers staying in the same place, would be a hang of a lot lower. On average, our way of reasoning with it is that you say that the customers that are of identical class, we give them a correlation of 1, and customers with of a different class, we give, between classes, we said that the correlation is 0. That's a practical way of working with it. It's interesting that the reason we make that reasoning is because it saves a hell of a lot of calculations at planning time. Otherwise, you end up with a matrix full of the sparse matrix, and the network traffic is just too high.
There's another question there.
Could you give some indication of what the scale of the different classes is in terms of the data points involved? Because that clearly must have some significant impact. You may have implied it, but I didn't.
By scale, do you mean consumption or the number of connections?
Well, I was thinking in terms of the actual data points that represented member of the class.
The number of customers that got into a load class, we controlled that stringently to have more than the 30. That was kind of our minimum. Otherwise, we couldn't go any further. In terms of the breadth of it, we were working with at least a year's wide of hourly data per customer. But it's interesting because if you look at how the customers are concatenated almost within the metering system, we had to join every customer to all of the metering points before we could model them. So some of those customers are worth 18 or 20 metering points. There's some that have over 100 metering points, actually. The very widespread customers in a particular area. But they're substantial, large farming operations and so on.